Hello and welcome back. In this video, we want to talk about the how, right? So about Six Sigma and about the how. So for instance, if you, the company, want to do Six Sigma, you're very interested, you know it's adding value to your production and you want to do it. What do you do? And this how part, rather than sort of leaving it to a brainstorming session and thinking from scratch what to do, the DMAC acronym provides a kind of a instant quick start, right? So it's like in Kaizen we have the PDCA, plan, do, check, act, right? So if we don't know what to do, well, just cycle through plan, do, check, act. Did I plan? Did I do? Did I check? Did I act? Right? Did I act on it? Action is very important. Take action, right? But DMAC here is just similar kind of acronym to get you started. It doesn't mean you must follow the template. And even if you follow the DMAC, it doesn't mean you are already Six Sigma, right? Remember, Six Sigma is very numerical, very data oriented, very statistically supported. And so you must have the numbers to support that you are indeed Six Sigma. You are achieving that capability, or you are Six Sigma certified, right? So DMAC here, what does it mean? Defined, measure, analyze, improve, control. DMAC. Define means customers and priority. So let's just walk through this story contextually so that we can understand and put in place what each letter is supposed to be telling us. So we are the maker of cereal. Consumer Reports just said that we are having bad quality. What is bad quality? Less than 15 ounces of cereal. Presumably, the stated amount is a bit higher, like 16 ounces, right? So if you read the specification, right, the cereal has a specification, right? Net weight 16 ounces, but 15 ounces is like visibly lesser. So consumers don't have to wait to verify, and then when they see that it's lesser, what on earth is again, right? Another box having very little cereal, let me weigh, and they found 14.9, 15.1 rather than 16 ounces. So enough complaints, you know, arise that gets published as a headline news, and then of course it becomes a problem, and so the company, what you know has to take action, right? So but what should we do? So DMAG. So how to respond to incidents, right? So DMAG say first, define customers and priorities. What is the critical to quality characteristic? Remember, quality is the specification. What is critical in this discussion? What's this complaint about? Oh, it's about the ounces, right? It's not about the cereal looking black in color. It's not that the cereal has a lot of husks, the empty shell, yeah, uh, mixed into the cereal. No, that's not the complaint. It's not about the taste of the cereal that is too sweet or not so sweet or whatever, right? So that those are not the quality. What's the quality? The quality is about the weight. So then we focus on the weight. Then we start to measure, right? So remember, Six Sigma is very numerical. Without data, you cannot do anything. There's no basis to support you from uh, for any action. So you need to measure in order to obtain the data. So how would we measure? Do we randomly sample from the factory, at our factory, before we ship out? Do we go to a random store, supermarket, to take our cereal from the shelf and measure? Do we call up the consumers who complain, right? So how do we do it? How do we sample, basically? Huh? What are the acceptable limits on this measure? So define all this. right? Suppose, now we give some examples. Suppose company says we must be within 5% of the weight advertised on the box, right? So the cereal says net weight 16 ounces, and the legal department says plus minus 5% allowed by law. Let's say that's the case. Then the lower control limit, upper control limit will need to be set at these or more stringent values, right? So 15.2 or higher, 16.8 or lower, to ensure that the production that inevitably will have fluctuations, right? And it is still within these legally permissible limits of the stated 16-ounce box. Then we randomly sample 1,000 boxes because you want a good feel of the reality, and then you get the sample average of 15.875 ounces, the sample standard deviation of 0.529 ounces. Now, I stress the word sample because these are the 1,000 measurements, and then maybe you use Excel, and then you do an average of those 1,000 numbers, you get the average. You do Excel and you do a standard deviation dot S, right, the sample standard deviation, and you get 0.529 ounces. And then we use these as what in statistics we call it as the point estimate. Point estimate. That means these are reflective values for the 1,000 boxes, correct? But the company produces 2 million boxes for the past month. Example, 1,000 is hardly representative of the 2 million, but it is also a bit of a destructive test, right? When you open up and you weigh it, you cannot sell it anymore. So we are going to apply statistics here and say that these 1,000 averages, they are reflective, they are accurate enough, okay? They are reliable enough to tell us what the population mean value mu is. In other words, if we could average the 2 million cereal box weights, it would have been very close to this randomly sampled 1,000 boxes of cereal. In other words, it may be 15.882, it may be 15.865. I'm kind of fixing even the first decimal place, so it's that reliable. Yeah, so it's reflective enough for us to be comfortably saying that, yeah, I know this average is for the 1,000, but we're just going to assume that this is also the value for mu. Okay, you understand that? Yeah, because estimating the population mean, the true mean, that is actually the measured averages of the 2 million cereal boxes, is always not possible. I mean, practically speaking. All right. So theoretically, we're just going to use the average of the 1,000 as the average of the 2 million. Okay, good enough. And that is also statistically supportable. If we use the average of 10 boxes, then we are not so steady. All right, we are subject to being accused of not having done enough of our investigation. But at 1,000 boxes, it is, even in statistics, it is acceptable, which means that even if you go to the court and the judge asks, what makes you so sure that your production is giving 15.875 ounces as an average weight? You have a basis and it is convincing. That's the sort of authority or status, right, or the power of this 1,000 box average. Similarly, for the standard deviation, yeah, remember in Six Sigma standard deviation, the sigma does carry a lot of weight. And again, we will have to tear open the 2 million boxes, weigh them, then use Excel to calculate, right? Then we get the sigma. Obviously, that is not possible in practice. So we're going to again use the sample standard deviation, what is usually recorded as little s, lowercase letter s, 0.529 ounce of sample standard deviation, we'll just assume, right, it is the value of the population standard deviation sigma. That's the sigma we are very interested in. All right. So if we have highly capable production line, 6 sigma capable production line, then this number would be very small, like 0.1 ounce, such that times 6, it is still 0.6. It is still small, right? Or 0.05 ounce times 6, it is still just 0.3, way less than the required 5%, right? So no issue if you are highly capable, right? But at this point, our fact reflects that the randomly sampled 1,000 boxes gives a sample standard deviation of 0.529. We'll take it as the whole population's standard deviation. So we just calculate, right? At this kind of assumed values for mu and sigma, first of all, what is the Z value? Then we can calculate what is the percentage of boxes outside the tolerance limits. Yeah, okay. Outside means defects. Inside means it is acceptable. Inside means good product. It doesn't matter if it's sour cereal. Doesn't matter if it looks blackish. The color doesn't look right, right? Because that's not a critical to quality measure. Huh? It just feels right. All right, so that's okay. Outside means not okay. But then actually outside is outside the production mean, right? Outside the production mean. This is the 14.11%. It's not okay actually, a lot, right? What is supposed to be the calculation should be outside of the specified 5% limit. All right, so below 15.2 and above 16.8, and that will be the sort of defect percentage. And that is exactly what we are calculating here, right? So at these numbers, with our actual production numbers, we measure them against our design numbers, let's put it that way, the right 15.2 and 16.8, and we realize that wow, that's 14.11%, right? So our production center is at 15.875. It has deviated from the setting of 16. Just imagine a production norm and say turn it to 16 and all the boxes will be filled with 16 ounces. Basically something like that. Modern machines are pretty much digitally controlled. So you tune it to 16, all the boxes will be filled, supposed to be filled. So we think it is 16, but ended up, right, after many repetitions, and then we, because it's 2 million boxes, right, having been produced, and we sample 1,000, and we realize that, hey, the 2 million boxes basically are centered around 15.875 ounces. Naturally, some of them will be heavier than this, some of them will be lighter than that, right? So long as they are fluctuating between 15.2 to 16.8, as our legal department had verified, plus minus 5%, acceptable, shouldn't have any complaint. And if people complain unreasonably, we'll still stand up okay in the eyes of the law. But then we calculate the percentage outside that is not okay, right? That means it's outside the specified design limits. And those areas, in other words, those probabilities, those percentages, they add up to 14.11%. That's a lot, right? That's a lot. So even if, that is, even if that is not reaching 20%, 50%, but that is to say they are not supposed to be sold outside. And no wonder there are a lot of consumer reports saying, complaints saying that how come your cereals are looking light, right? So company realizes maybe it's our fault, right? Then what do? Well, analyze. So DMAC, right? So analyze. Oh, okay. Well, we need to take such corrective action. After analysis, we should decrease the variation. So obviously our as in this cereal company's sigma the 0.529, is a bit large, right? Because the plus minus 5% here is about 1.6 ounce. If you take sigma times 6, that's about 3 plus ounces already. So this is probably 2 plus ounce, 2 plus sigma. Very bad compared to 6 sigma. So you need to decrease variation. But this part is easier said than done. As I said, if that production machine, it's just one machine, and you find that particular part that is having a rattling cover or whatnot that's causing the variation, very easy. But unlikely it is that easy, all right? Unlikely, because it would have been fixed if it's so visual, so visible. So we will have to investigate, but at least we now know the direction, decrease the variation. We are definitely not 6 sigma, right? Not even 3 sigma, I think. We also need to center the process. What's this? We said 16 ounce. Who allowed our production to deviate to 15.875 ounce as the mean value? Of course, you're going to create a lot of waste, right? Because if you center at 16, then it's just a matter of the sigma. But then even if we do the sigma right, you are centering at the wrong average. And of course, you're going to create a problem, right? Yeah, so why start off with the wrong center, right? Nobody understands that. So we have two problems. We need to decrease variation, center the process, and then we need to increase specifications, perhaps, right? So after some discussion. Okay, then what do? Well, we need to improve, right? So remove the causes. Analyze means find out the causes, the theoretical causes, the big invisible picture, right? The sigma is the problem, the shifting of the mean is the problem. Remove causes. On this part, you're going to spend money, right? To remove, you really have to maybe hire consultants to figure out, investigate. I maybe also investigate so as to improve. Where is the machine that is giving us a problem? Or are there multiple machines? Or is there machine plus operator, machine man kind of synchronicity issue? Is this an operational issue, right? That the training issue, so on. And how good is good enough, right? So you've got to try to improve to what extent? Well, famous case study is, of course, from Motorola, who started this Six Sigma. Do you know what Motorola manufactures? That's right. They were famous for their pager, paging system. In fact, they started with walkie-talkies, right? So, and then they were developing into the telecommunications. So different regulatory systems. Walkie-talkies, you just talk in private, but to go on to pagers now is definitely obsolete. But pagers were the physical devices. It's a bit like a device that can only do SMS that we know of today. So, and it's one way. You got to call and tell the operator to send some message, and then they will help you deliver, right? Or later on, it evolved to you can try to call and page for a person by very, very short encodings and all that. But it's basically outdated. They were doing well. They were doing those devices selling worldwide. So they need to manufacture quality devices. What are those? Something similar to what we expect our phones today, right? If you drop it accidentally, it shouldn't break, right? The plastic should be robust. The electronics should still function. The LCD, it was LCD. LCD screen shouldn't break, and so on and so forth, right? So how to do that? Motorola first instituted this discipline called we need to be Six Sigma. So that's all the development of Six Sigma follows from that. So of course they have developed their own internal policies, guidelines, disciplines, training manuals, and all that to do this and to actually implement them, enforce them, measure them. So being an American company, very scientifically driven, very data driven, right? So a lot of statistical control, in fact, Six Sigma itself suggests very strongly of the statistics that go behind in terms of supporting the reasonableness of this Six Sigma thinking. So they insisted on 2 parts per billion, right, allowed. Notice that they also never say zero defect. The very Zen style, like Kaizen style, Kaizen and Zen will be very different. Different kanji, different character and different meaning altogether. In Kaizen it's more of aim for perfection, right? Never stop, even though we quietly know that perfection can never be met. We never say that. We will ever, forever aim for towards perfection. That's the Zen thinking, right? So, but then for Six Sigma, they write it down on paper, right? That we follow what normal distribution tells us. It is not possible to aim towards zero defect, but 2 per billion. We're just saying small. But how small is small? They actually can give you a number. So if you manufacture 1 billion Motorola pages, at most we should find 2. Maybe if we are good, we might find 1. Still, we are Six Sigma qualified. So that's the Six Sigma. Okay. Now, what's interesting is also this observation that the production will shift. That's what you normally might read as the process center shifts. What does that mean? So, like the example we have seen, the specification says 16 ounce. Of course, that can also be a 16 centimeter long Ultraman, a 16 centimeter wide cake, so we can define, we can specify. That's our design, right? And when you actually configure, whether it's human or machine, you tell the workers, please do measurements and all that. So whatever it is, the production line comes out with a measured center at 15.875 ounce. So this is the observation that is measured coming out from the process, coming out from the production. So that is the observation that even though we configure it, we specify it, we fixed it, we program it, whatever, due to 2 kinds of variations, right? Common variations, assignable variations. Turns out that the process will also not only fluctuate, but bias, move to one side. Okay, this will be due to various things, due to the variations being created asymmetrically, right? Maybe it is wobbling, but it is wobbling more to the left than to the right. So of course, right, at some point, the center will shift to be 16.5 ounce, more to the right. So it's like it has more impulses to the left, and so it brings the machine tilting it to one side more often than the other side, and so on and so forth. You can understand. Yeah. So due to the variations themselves, it can cause a permanent shift, a bias off the center. Now, of course, a bias off center can also due to many reasons. Accidental touching of the configuration, didn't update the software, whatever reasons. So no matter what, production is a complicated suite of activities that is in some sense unnatural, especially for human, whenever human is involved, right? It is asking us to repeat the same thing precisely all the time, never making a mistake. I mean, that is true, right? For operations, that is true for making flow units to spec all the time. That's true for quality definition, but that's very unnatural for humans. So for robots, that will be due to various fluctuations, humors, right? Due to the physics of Earth, there's no running away. There will be magnetic, fluctuations here and there. There will be electrical fluctuations. There will be mechanical vibrations. However, slightly, it may be imperceivable. No, there isn't any. There's no earthquake, but there may be certain kinds of influence, right? Disturbances that we may not see, but the machine kind of feels it, gets impacted, and then gets biased. So no matter what, center shifting is a observation that is true or that is on records. So we are saying, or Motorola is saying, with 1.5 sigma shift in either direction, yeah, I've already quoted many potential reasons, right? So in either direction, and it's reasonable to say it may be to the left, it may be to the right. You can't tell. It's a bit random. The process will move. Then it implies that we can have up to 3.4 million bad or defective products being produced. 3.4 parts, sorry, 3.4 defects per million. So from 2 per billion, 2 per billion to 3.4 per million, even if you put this as 2, then you will see that there's an increase of 1,000 times of defect rate. So 3.4 parts per million. So that means we allow up to 3.4 defects per million flow units being produced if you are Six Sigma and allowing for a 1.5 sigma shift. Why 1.5? Well, in Motorola's experience, that's the extent of shift permissible or is common. It's like you cannot do away uh, with this amount of shift, of possible shift. So so this is the lesson learned. That means we know that the center may shift, hopefully won't shift, but then it is observed that things will happen that way. Then we should expect to have 3.4 parts per million being defective. So that's the improvement part. Improve until we see so little defects per million units produced. Yeah. And finally, control. Control in this case means steer your steering wheel left, right, and maintain the quality. In other words, maintain the centerness, right, of your driving direction. So when we drive, whether you drive or you ride a bicycle, somehow you notice your hands have to jitter left, jitter right, move left, move right a little bit. Turn the steering wheel ever so slightly, a bit left, a bit right. No, a bit left. No, a bit right. A bit right more, and then a bit left, right? But why? Well, because variations. Some forces, partly variation, partly other things. Maybe the axle of your car, maybe the steering of your bicycle isn't fully aligned, isn't fully locked with your wheel, whatever it is, right? Your wheel may be also deformed, reshaped ever so slightly. We don't know. Due to all these unknown but ever-present factors and reasons, we have to maintain control by steering left, steering right. So this control here means keep your steering wheel straight, right? Maintain. And you cannot leave your hands there because it will start to bias. So that's the idea. So to do this, we need a lot of help in terms of collection of data. So without data, you cannot talk about Six Sigma. So statistical process control, right? Use data from actual process. Even the word is mentioned here. Collect data. To do that means in operational, in production sense, measure. All the time. Don't measure only at the end. Remember, total quality management. What does that mean? Customer center, but also quality everywhere. Quality is built in to every part of the process, not just throw away the defects at the end of the production line. Then there will be a lot of waste. That will be very expensive regardless. But then from the lean's perspective, you are generating a lot of waste. That's upfront the first thing that we will say, rather than that's very wasteful. That's from the monetary perspective, the layman's perspective, right? So the lean perspective is, no, don't do that. Build in the quality in every station by collecting data, estimate the distributions, look at the capability. All right, is reducing the sigma, that means good quality, is reducing the sigma of that machine typically. Human tends to be harder, is reducing the machine's sigma. That means increasing its precision, reducing its vibration, reducing its inaccuracies. Is that possible? Or is there a fine-tuning knob that allows us to do that? Is it possible? For human, some sort of a slight improvement could be based on training. Train more. For example, sign your name 100 times and it should all be having the same T being crossed at the same position. Well, you're not going to be able to do that right away. So you practice signing every night until you have done that 1,000 times. Then maybe, yeah, so with training, with repeated practice, and maybe with supervision and guidance, possibly with carrot and sticks, right? If you don't do that, you don't get your dinner. Right? If you can do that, I'll give you $1,000 bonus. Okay, good, right? So maybe so those are for human resources or operations. And if it's for machine, most likely you have to look at software improvement, upgrading, buying accessories, yeah, cheaper options, and of course the ultimate step is to change the machine. Statistically monitor the process over time so that you build up what we call a longitudinal observation. That means across time. There's a time series. There's a time series for you to see the dots. The dots should be random, right? Up and down in no particular direction. And that is just noise, which is the best state we can hope for, right? But if the noise is huge noise, amplified noise, then it will tell us something, that there is noise, fine, but then it's amplified. Why? Who amplified it? Which part, right? Amplified it. If you have longitudinal, that means time series, over time you see the data, you can see trend, you can see gradient. So is it a consistent day after day rising? In a very disciplined manner, every day is rising. How come? There must be something that's creeping along, right? Yeah, because otherwise it should be sometimes rising, sometimes falling, and then rising some more, dropping a little bit. So most of the time rising magnitude is higher, dropping magnitude is lower. Therefore, in the end, after 10, 20 days, 1 month, 2 months, it has gone up by a lot, though all the time is highly random. Yeah, so all these are different patterns giving you a sign of a signal of what potentially the problem can be. It's like the doctor attaching a device to want to record and measure your heart rate all the time, in real time, all the time. That's statistical process control. And there's not much to be done. But then if you don't measure, the doctor cannot see the trend, right? So that after, of course, certain diseases, they can be diagnosed or it's exhibited by the heart after several minutes of measurement. So you just lie there for a few minutes, missing heart rate, right? Or rapid heart rate all the time, even though you're resting, you're not doing anything, you're beating at 120 beats per minute, as if you're running slowly, or you're running quickly, like 150 beats per minute. You're running very quickly. What's happening, right? So something, or you are having slow heart, or you are sometimes fast, sometimes slow. Like the first minute is very fast, second minute is very slow. Now, what that will be a different kind of disease, different kind of problems. Or you're having a missing heart rate, so the heart rate is 65 beats per minute, very healthy, but ever so often, the heart stops for 1 beat and then continues. Right? Oh, that's dangerous, right? Who knows after it stops, will it continue or not, right? So all these things are like basically what we are interested in as well in our production line. What's the heartbeat of that station, of every stations, right? So we have multiple hearts because all the stations are operating, right? So we're going to monitor each and everything, each and every heart, each and every station for its for the critical to quality measure and more, because we might not know what is important. So so the serial we mentioned, That's due to complaints, right? But then when we are producing, we actually will measure several things. We may measure the weight, the height, the length, and before packaging, we might want to that the final step before packaging, we might want to look at the color of the cereal, right? Use camera to take the color, use AI to check the color, use AI to detect if there is any husk that will spoil the taste, right? And we may also want to randomly sample to check uh, to analyze the nutrients. Is it too sugary, right? Has it got enough vitamin B12 and so on and so forth, right? Because we claim that it gives certain nutritional contributions to your body's health. So statistical control in full strength, right? In full power for every single station. So that if there's any disease, heart disease, remember, then you, the doctor, the Six Sigma expert, can quickly detect. So this part actually very important, right? Very data collection is at the core thinking of Six Sigma. Without data, it's not Six Sigma thinking, right? So I'll leave you with that. So hopefully you have some idea of what DMAT does, right? And that is basically an illustration of what typically one will have to do, right, to start off and maintain and run the Six Sigma quality control schemes. In this final slide, we are observing a company who says, wow, Six Sigma, right? I'm really interested. What are some of the things I can use from Six Sigma theory, lessons, discipline, course, what have you, right? You have seen many of those Six Sigma things. What are the ready tools that I as the company can use? What are the ready ones? Because I don't want to reinvent the wheels, right? And you shouldn't. And if you quickly look through these, they are very similar to the Kaizen tools, some of them, most of them, right? To the Kaizen tools. And not really surprisingly, because both are trying to look at quality in the same way. Did you meet the specifications? Yeah, because if that measurement, that definition is not in sync, then the tools will be doing different things, right? But of course, fundamentally, both are very different. Kaizen, for example, of course, almost all theories will want to look at data. So Kaizen, sure, with data is good, but then the center of thinking for Kaizen is to take the initiative, to have the constant discipline to always want to do better. And then you talk about how to do better, what are the tools to help me do better, right? But Six Sigma, the core of everything is data. So we'll see. First is flowchart. Flowchart lays out the flow of the defect detection, correction, and remedy procedures. So materials received, inspect, right? So is that a defect? I mean, that's very simplistic, right? If there's a defect, do we fix ourselves, right? Maybe if it's simple, we fix ourselves. We return to supplier for credit, or we ask supplier to come and fix, maybe, right? So all these are the flowcharts to find quality problems. So that remember when the flow chart is drawn out like this, you and I, maybe hired as temp staff, can go inside the company, the factory, the production floor, and immediately understand, right? So that's the power of visualizing the flow of the flow units and of course the flow of the defect handling procedure. Pareto, we have seen it before, yeah, in Kaizen, 80-20 rules. So 80% of the time, right, can be 80% of the problem is due to 20% of the departments in this case. Okay, so design in this case, in this chart, design accounts for 80% of the problem. So we have a bad designer, right? So the product always gives problem. This designer only sees what the customer wants and never tries to or builds into the design the ease of production. So a good designer for a new product not only must listen to customer, of course, from TQM we remember to listen to customer, but you also must help the producer, right? Because you're working in this factory, you are the link between the customer's whims and fancies and the producer, your factory's capability. If you're unable to produce high precision toy, then don't design high precision toy, right? And so designer here is very important, at least according to this. But only if you collect the statistics, right? Because you cannot draw a Pareto chart without collecting the frequencies and the causes, right? Who is responsible for this defect? Which department? Oh, design again, right? So if you do this, then you realize that, okay, let's have a meeting with the CEO and let's decide what to do with design. Should we split it apart? Should we hire somebody else? Should we have an internal QC to check the design first? Whatever it is, we are focusing our resolution attention on the low-hanging fruit, right? If we can solve design, we are solving 80% of the manufacturing problem. That's the idea. Then we look at check sheet, right? That wasn't really there. Check sheet here, right? Billing errors, okay? Okay, so instead of saying there are all these defects, so each line, of course, after 4 lines, you put a 5th line so that it is easy for counting, right? And if you see a cross, it just means this is a set of 5. It's easier to count locally, like 1, 2, 3, 4, 5, right? 1, 2, 3, 4, 5. It's easier to count locally than when you have many vertical lines, then you do lose count, right? So I thought that's what they do in prison as well. Huh? So another day, so I draw another line. After 4 lines, then you cross, and it's easy to count how many days you have gone through, something. Okay. Rather than saying collectively, no, just one account, one number, in total, how many errors, how many defects in the accounting firm. So notice accounting is a service. Yeah, accounting is a service, but accounting can have defects as well. What are the defects? These are the defects. Wrong account number. Okay, so maybe this particular station in the accounting department, they are in charge of looking at the raw receipts and then entering those receipts into the computer system. So in the end, the audit department will check or double check, and then they detected problem. Okay, so this one is wrong because of wrong account, so put a vertical mark. This one is wrong because this transaction was recorded wrongly because, account is right, but amount is wrong. So if you start seeing many vertical lines here, for example, just to emphasize a little bit, what is the picture telling us? It's a bit like histogram, right? Yeah, this is like a horizontal histogram, similar, but it's trying to say that don't lump them together. Try to categorize them into subtitles of the defect. Don't just say it's billing error. Don't just say it's a accounts receivable error, but break it apart. Is it due to wrong account or wrong amount? If it's due to wrong account, and that is also true for accounts receivable, then maybe is it true that the account number is too small on the computer screen? That's why it's always very hard to visually verify. Yeah? It has to point to something, right? When this particular bar on the bar chart here is particularly highlighted, yeah, and very long and significant. On the other hand, if it's wrong amount that is causing the bar to be very long, then maybe is it that the computer screen, yeah, it's having a very tiny font for the amount to enter, right? So, and that's true only for the AR data entry screen, and that's not true for the rest of the screen, right? So we can then fix the problems at the source a lot quicker than if you lump everything together. Yeah. Okay, so next is histogram. Histogram, basically all these are also histograms, Pareto chart and the check sheet, right, using the vertical bars. And histogram here refers more to those with numerical measures that on the left is lesser than on the right. So for example, defects in a lot, that's comparable. 0 defect is better and is lesser than 4 defects in a lot, right? So we like to see histograms like that. When you have a histogram, it reviews the frequency, number of lots that have these characteristics, right? You might not know it, but histogram showing the frequency on the vertical axis and numerical numbers on the x-axis. Histogram is a bit like X-ray for statistics and data in general. So when you do X-ray shows what your eyes cannot tell, right? If you look at your body, your flesh, your skin, if it's darkened, you kind of can guess that, even if it's not your body, right? You kind of can guess that the person must have been hit hard. That's why it's black and green and all that. Yeah, so you can visually detect defective skin, right? But if there's a crack in your bone, if there's a micro fracture in your bone, you can't tell, right? If there's a debris, your bones are cracked into multiple pieces. There's a tiny little bone so sharp that it's hitting your nerve. That's why you feel pain all the time. You can't tell. Why am I painful? Is it that my muscle is having problem? But you need X-ray, right? So X-ray reveals those things that you can't tell. Similarly, I would also venture to say that histogram reveals those kind of pattern invisible in the data but ever present in the data that you can't tell. If you look at the data, our eyes are quite ready to see differences in averages. For example, if you look at a crowd, right, you can see people who are taller, who are shorter. You can visibly tell, but you can't tell the sigma, the standard deviation of people. You can't visibly tell, right? So you also can't tell whether there tends to be more people who are medium height than lower height or taller heights, right? So you can't tell the frequency of occurrences. Oh, there are a lot of short people around. I mean, if that is 80%, then of course you can tell. But if it's all kind of evenly mixed up, can't tell, right? But then when you plot the histogram, if you can plot the histogram, that means you measure the heights of everyone and you plot the histogram, it readily shows that, oh, these people, most of them are medium height if the x-axis is height. Yeah. So the histogram reveals what is not so visible to our eyes and to our to all the measurements. So you only have data, right? But you plot it into histogram, it shows in this example that most of the lots, or like most of the lots, the mode, right? The mode is the highest frequency. Most of the lots have 2 defects. Some, and not insignificant, quite a number of them, have as high as 4 defects. And there's no lot that's having more than 4 defects. That's strange, right? Yeah. So we might want to investigate. How come stopping at 4? Why so strange, right? And how come there is few lots having 0 defect? I thought we have a QC department. Why 0 is so little? No, doesn't look right. Maybe we are expecting something like that. 0 defects, having a high frequency, then maybe 1 or 2, slip through the cracks, and then getting lesser and lesser, and then that's it, 1 or 2, but no 3, no 4. We expect this kind of like deep slope, right? But this will reveal some very strange pattern that is totally unexpected, right? Yeah. So if you think through, the right logic is it should be this descending exponential curve. Maybe, right? So we would think that, but having a normally distributed curve, very strange. Something is wrong. So again, it reveals the invisible. This kind of defect, this kind of problem, like a normal distribution of defects, number of defects, right, in the lot, uh, could imply something that is very hard to detect. So now armed with this evidence of the histogram, then we can go about very confidently and say something is wrong. I'm going to inspect from head to tail to find out what's going on. Something is really wrong. It's not just a gut feel, it's a data-driven activity. Cause and effect, fishbone chart. Okay, so that was from Kaizen. Yeah, and definitely, right, Kaizen has ownership of this. So cause and effect, the Westerners will call it cause and effect, but Toyota calls it fishbowl. And we talked about it in the Kaizen session. Basically, is to give us a way to start looking for possible sources of problems. So we found a defect. The effect is being felt, right? We found a defect. Go backwards. Remember, Kaizen also said use the 5 whys. Why, right? So we keep asking the 5 whys in addition to using the fishbone chart, prompting us. It could be man, machine, material, method, the 4 M's, and the 1 E, right? Environment, right? So man, machine, because they are the resources. It's either human doing things, resources doing, machines doing things, or human operator operating a machine doing things, right? So that's man machine. It could be problem due to the material itself. You're using a plastic cutting machine to cut a steel, or the plastic that was supplied by the supplier had a protective invisible wrapping that is quite hard and is denting our plastic cutting knife. That's the material part, for example, right? Yeah, so men, of course, lack of training, not alert, whatever it is, right? Machine, second hand, used for a long time, not properly maintained. But material, yeah, so we just, it could be due to material. Is it due to method? The method of feeding the material into the machine, right? I had this experience. This super duper heavy duty Hewlett Packard printer, right? That is used by the university. So uh, there was once during the long vacation, right? So I had the need to print some lecture notes. So I went there, I print. It was not printing. That's a defect, right? So it was not printing. So I investigated. Oh, lack of paper. Okay, fine. So I found paper. Luckily, they always have very well stocked paper. I open up the stack, just find a slot, insert it. And the man, the operator, me, no problem. Machine, well, cleverly saying, I detected a problem, no paper. Good, I will fix it, right? Material, very good paper, ATG, right? Feed it in, still defect because machine still says no paper. And I was like, are you crazy? You know, I fed the paper, it's brand new paper, and I checked there is paper, and then I checked everything again. There are so many trays. There's tray 1, tray 2, tray 3, tray 4, tray 5. And then there's a side tray. So I conveniently opened the side tray because it was meant for, I don't know, a second backup A4 paper slot or something. So I opened that because there's a A4 slot. So I opened that, I put in, and the defect, that means the printer stopping due to lack of paper, the defect didn't go away, right? So I put in everything only to realize, oh, the printer's default is tray 2, right? Okay, so that's the other side. And of course, I won't take out what has already been put in. So I kept that and then opened up a new rim and I fed into the right tray. This time, everything works. Now, what's the problem here? The problem is with the method, right? the method of feeding it into the tray. Is that I knew how to feed the paper into the tray, but it's the wrong tray, right? And and you cannot blame me because I was feeding it in there, right? And there was no manual. Not that I'm saying there's no manual. Even if there's manual, I probably won't read because, come on, it's supposed to be so straightforward, right? So wrong assumption by me, and perhaps right. If I can blame, then I might say that the indicator should say tray two rather than lack of A4 paper or lack of paper, so it should probably give a bit more hint, being such a heavy duty, sophisticated, expensive machine. It should tell me more, right, when it detected so much about its internal operations. And finally, the environment. So man machine material method, and is there a defect due to environment? So it could be that that the cake that is being baked, right, is failing the quality test, right? It tastes a bit sour. Don't know why. Okay, so everything has checked out. Person is experienced. Machine is operating well. Material, the flour, the egg, the water, everything is high quality water, right? Spring water even. Method of doing the recipe is clear. In fact, it's done by mixed by a machine and baked by a machine. Everything is fine. So what's wrong? Oh, the environment, or the air has got high humidity. So when the flour gets, or the yeast, when you open up, right, and it gets exposed to the air for more than 5 minutes, it starts to turn into some sort of a soury chemical that is going to cause diarrhea or whatever it is. So I'm just saying that environment can be the problem, even though no one made any mistake, no defect is visible. The environment, chemical, microchemical reactions is taking place, right, in an invisible way. So all these are good prompts that when we sit down and our mind is blank, it's costing the company a lot of loss in profits, right? So what should we do? And our mind is just blank. Right? And then when we go through these fishbone bones, it's prompting us to check. Yeah, it's guiding us, so it has that benefit. Control chart. This, of course, right? Lower control limit, upper control limit. That's like the core backbone of Six Sigma's success. Without that, without collecting data, without what I would say the time series here, right? The longitudinal visibility of the behavior of the pattern, right? So each LCL, UCL, each such chart is for one critical to quality measure. So in our previous example, critical to quality was the weight. So then weight has one such chart. If the color, right, say measuring the color, right, from black to white, example, and the cereal should be on 0.7, then the color will have one such chart. Then you develop a UCL, LCL around 0.7, yeah, and any others. Okay, the number of husks being found in per package, yeah, and so on. So every single measure will have one such chart. The more you have, the better. But then of course you got to, spend the extra time, get the extra machines and sensors and measurements and networks and maintenance going to build up this database of time series of all the measurements. So this way, I mean, this way of doing things, having many critical to quality measurements, is a bit like doctor measuring your heart rate. Whereas measuring your risk heart rate only involves one measurement. Some of those ECG and EEG, they start to attach many probes, right? Yeah, many probes along various parts of your bodies, because the electrical signal will take microseconds, milliseconds to go through, and then they can also deduce from the the delays or the lack of delays, or the performance of the heart rate at various parts of the body simultaneously, and contrast them, right? So the more data that that kind of EEG, ECG collect from your body, the presumably, and logically, the better in-depth analysis the expert, in this case the doctor, can perform. Of course, if the doctor is not trained, then you cannot do anything, even if you have the data, right? So same thing here. You need to be Six Sigma trained. You need to be using all these tools. You need to enlighten yourself, to open up yourself to the possibility that, what's the problem? How come there are red dots here, there are red dots there? How come it's symmetrical, right? You need to like open up to these questions and ideas, maybe using various of these tools, fishbone chart and whatnot, or better still, merge it with Kaizen, right? And then start to find the cause. And then, by maintaining uh, these measurements to ensure that they all stick within the lower control limit, upper control limits, yeah, and then you are then able to uh, claim that you are having high quality production. Okay, so in summary, Six Sigma tools, they talk about uh, the reduction of variation, right? The removal of course, fluctuations and or therefore waste, and finally, using the total quality management, right? Customer centric, and of course, implementing quality at every single point in your production, rather than saying, okay, we only measure or do Six Sigma at the end. So all these are central to Six Sigma. Very, very core to Six Sigma success is the collection of data. So you definitely need to collect data. And of course, in these days of AI, we can also, use uh, LLM, large language models, to train, right? Because you have the data, you can then train the AI to diagnose and say that when you see this pattern, the likely causes this, right? So it can even help in terms of, so the data that's collected from Six Sigma implementation can also used to feed into AI to train the weights, so that you can have an AI assisted Six Sigma. Of course, those are futuristic thinking. But let me just leave you with these tools, and then that's all for this session. See you in the next video.